All right, so let's do another example problem. Let's say that we've got small room, has two objects hanging from the ceiling. Okay, M1 and M2. Okay, and so we have a tension T1 and T2 there. And so let's say that M1, okay, is going to be equal to 1.75 kilograms. And let's say that M2 is going to be equal to 1.5 kilograms. And so I want to know, what are those two tensions? Okay, so pretty straightforward. Two objects hanging here. And so what I want to do is free body diagram. What is this? Okay, so this was going to be the M1, that's going to be M2. So I want to know that. So free body diagram, we have T1 pulling up, we have M1G pulling down. So T1, if it's just hanging there, acceleration is 0. So T1 equals M1G. And so that's going to be equal to 17.2 newtons. Plugging in the numbers that I had. Plugging in the 1.75 kilograms there. Okay, so what about for the other one? Free body diagram. I have T2 pulling up, but I also have T1 pulling down, and I have M2G pulling down. Okay, so that means that, again, if acceleration is 0, then T2 has to balance the downward forces, T1 plus M2G. Okay, and so that would be equal to, again, plugging in the numbers we had before, 31.9 newtons. All right. Well, there's another way of solving this. Got T2, got T1, M1, M2. What if I drew the free body diagram for the whole thing? Then what happens is I've got T2 pulling up, I've got gravity pulling down M1G, I got gravity pulling down M2G on my system, so T2 has to be equal to M2G plus M1G, and so M1 plus M2 times G, and if I plug in the numbers, I get the same answer, 31.9 newtons. So it doesn't change. Okay. Now, what if, as I said, this is a little small room. What if the small room is an elevator? What if the elevator is going up at constant velocity? So acceleration 0. Well, if acceleration 0, sum of the forces equals 0, which means that force up equals force down. This is a concept that we're going to call later on in the semester equilibrium. The forces are balancing. Well, that's exactly the same situation we had before, which is exactly what we solved before. So what that means is that in this case of zero acceleration, constant velocity. So the velocity is constant. It's moving, but the acceleration is zero. So everything is exactly the same as before. Your book uses the term inertial reference frame to describe a situation like this in which everything is moving at constant velocity. Acceleration is zero. But what if acceleration is not zero? So what if this thing is accelerating upwards, and it's accelerating upwards at 2.22 meter per second squared? And so I want to do the same problem here. I want to find the tensions. So now I'm going to do the free body diagram for that bottom one. So free body diagram. So we have a downward force M1G. We have an upward force tension, but I know it's accelerating upwards. So that means that sum of the forces has to equal MA. So T1 minus M1G equals M1A. Okay. The tension's positive because that's in the direction of the acceleration. I'm going to say up is positive, okay, because I don't like minus signs, so I'd say direction accelerating is positive, okay. The weight is in the other direction. So T1 is going to be equal to M1A plus M1G. So T1 equals M1A plus G. And so T1 turns out now to be equal to 21.1 newtons. So it's a little bit more than it was before. What about the other one? So free body diagram. We have T2 pulling up. We have T1 pulling down. We have M2G pulling down. And so this is going to be T2 minus T1 minus M2G equals M2A. This is still accelerating at the same. So T2 equals T1 plus M2 times A plus G. So T2 comes out, after you do the algebra, 39.1 newtons. Okay. Well, notice what's happened here. As this thing is accelerating upwards, then in order for everything inside to go with it, as if G, in other words, all the equations were, we had calculated what the equations were when it was not moving. And so if we change the G to G plus A and plug into those equations, we get the new answer. So as this thing is accelerating upwards, it's as if we are increasing G. So now the question would be, what if it's moving upwards but accelerating downwards? What would happen? Well, what do you think would happen? What happens is, wherever we used to have a G, it becomes a G minus A. Okay. So it is as if acceleration is less. In fact, this is actually one thing that NASA does, that if before you put something in space, because it's very expensive to put something in space. You're talking in the hundreds of thousands of dollars per pound to put something in space. And so before you put it up there, you want to test how it behaves in 0G. And so what they do is they have an aircraft that goes up and arches over so that the downward acceleration is G. Well, that means that inside all the tensions are going to be mg minus g, or m times 0. In other words, it's going to be weightless inside. And so it simulates a weightless environment inside the aircraft. And so this is how you test things before you put them into space.